So let's then begin with the first of these topics, field maps. What do field maps look like in the magnetic field case? So now a typical field map will look something like this. So magnetic field maps. Now at present, unfortunately, we're only familiar really with the magnetic field from one particular case, which is our classic current carrying wire. So here I have my wire carrying my current here off to the left, as I so often do, some current I. And what we've determined so far really is that if we are at some location above this current carrying wire, here's my x-axis and here's my y-axis, that at a given distance above that wire, we know that the magnetic field points inward. So that's the magnetic field B. And certainly, because this wire is infinite, no matter what location I might sit at, because I never really see the edges of an infinite wire, the same arguments are going to apply, and once again I will find that the magnetic field is always inward wherever I am along the wire. We also know that it's inward if I go to a closer distance, right? The field's just going to be stronger. So the magnetic field is always going to be inward, as I indicate by my standard X convention, like so. Now, what about below the wire? Well, there are a few ways of trying to visualize what would happen below the wire. One thing that you will see, right, is that it's a little difficult to try to imagine, but if I were to try to view this wire here edge on, so I'm going to take a perspective here, I'm kind of sketching my eyeball here, right? I'm going to try to look here towards the wire along that direction. So what I'm showing down below here, of course, this is the side view of the wire. On this side, I'm going to draw for you the head-on view. And when we view this head-on, what we see happening is that we're looking right at the wire, right? The wire is pointing directly towards us, so that gives us our direct perspective. So let me draw then a dot here that represents for me the location of this wire, like so. And then I'll draw a little line around it. This is my standard symbol for something coming out of the page at us. This then is the current I. And if you think through the geometry carefully, when you're looking like so, and if the vectors are going into the page, right, you will realize that these vectors are pointing towards your left. So anywhere above this wire, up here, I have magnetic field vectors that are pointing to the left. Now, certainly as I get further away from the center, further up along the y-axis, the length of those vectors is going to be decreasing, like 1 over the distance. It goes like 1 over y. And then this is the view that I would be seeing if I were looking here from this perspective straight down along this line. Now, let's think about the symmetry of this case. Now, certainly physics doesn't depend on how you hold your head. So what I'd like you to imagine is, as you're looking straight down this wire, I'd like you to now to start rotating your head about this axis, right? And as you tilt your head, what you're going to start to see is that the locations where we're looking at this field, right, are no longer along a line that's pointing here straight up, but that line starts to appear at different angles as you're beginning to rotate and tilt your head. If you tilt it at 90 degrees enough, you'll see them coming along this way, and so forth. And if I manage to turn my head 180 degrees, right, or turn the whole screen upside down, if you kind of follow what will be happening continuously, as I would go from, say, a 45-degree angle like so, to a 90, to a 135 turn, till I get to all the way to a 180 turn. If I've just tilted my head a little bit so that this line now appears this way, what I would see then are the same vectors of the same length, right? But always perpendicularly to their axis. And now, because, the physics doesn't care which way I happen to have turned my head, we now know that if we had just started the problem with my head turned at this funny angle, then the field lines, the field values I would have seen at these points would have been exactly the ones at these points, but rotated with both their locations being rotated and their directions being rotated directly as I've indicated. So then I could continue this process all the way around to the 90-degree case, like so. The diagram is going to get a little busy here, so I'm not going to draw this vector again. I'll just draw it down here at this location. And then the shorter vector, that's a little further out. I'll draw also what happens if I continue the process as I rotate around here. Again, I'll skip the larger inner vectors because they're all starting to overlap with each other. I'll put the outer smaller vector here as an example. And then finally, I have that outer smaller vector and his somewhat larger inner vector would look like so. So I've now given you, there's one more here I can draw, of course, for you. This shorter one further out and the longer one again. I guess I can draw one longer one here. Might look something like this. So what you can see then are that these magnetic field lines tend to, or the magnetic field vectors, I've drawn a field map. I've given you the bases of vectors and drawn the actual vectors at each of their bases. I think you can see what this pattern is going to look like. So that's a field map. Now, of course, once we have a field map, the next thing we want to do immediately is to think what the field lines would begin to look like. So let's consider those. They're most easy to visualize, certainly in this head-on view. So recall the definition of a field line. I have to basically draw a curve or a line, right, that goes through, that follows always in such a way that it is always tangent to the field vectors. So you can see what's happening is I'm always moving or directed to move by these arrows. I'm always moving, my curve always moves in such a way that it is always perpendicular to the radius. Well, we know what geometric figure that represents. That represents a circle. So you can see I will have an outer circle here. Connecting of the circle is not coming out particularly pretty, but I'd have an outer circle here and an inner circle like so. So you can see that what's happening is the field lines then are coming out to be circles for the case of a wire. So that's our first thing that we've learned, is that the field lines are circles in the case of the infinite wire. That's our first example. So we've got a sense then, at least in one particular case, of what the field lines look like. Now, circles are nice. We know that they are circulating around my wire, which means if I want to fill in my side view, right, they are going into the page on top, but then they circulate around back of the wire and have to be coming out of the page in front. So my field map here would look something more like this. But there are, of course, two different ways I can draw circles to circulate around my wire. Right? The circles are all centered on the wire, but they could have gone in two different directions, basically either clockwise or counterclockwise. And the way we can tell which way they circulate is there are circles in the case of a wire. They circulate around the wire in one of two directions. And that's determined by the right-hand rule. So according to right-hand rule number 2. And in this right-hand rule, what happens is you put your thumb along the direction of the current, right? So in our example here, we would either point our thumb here off to the left, right? And then, or in this example, we would have our thumb pointing straight out of the page. So the thumb is along the direction of the current. That would then imply the fingers point which way you need to circulate around your wire. In fact, your fingers kind of naturally, if you're making a fist, naturally have a curved shape to them. So the fingers actually become a model for the field lines. So the thumb along the direction of the current, and then the fingers circulate or point in the direction of those circles, of the circulation of the field lines. Very good. So we have our first set of results for what field maps and field lines look like in the magnetic field case.